Okay, so in Chapter 8, we are going to be looking at sample means and how we can use those to estimate population means, because usually we don't have populations to deal with. So, so the basic idea behind a sample mean is, for example, we have these 5 players on a basketball team, and that's the entire population. So we can take samples of all of them, and we could have different size samples. We could have sample sizes of 1, and here's a sample, 215. Here's a sample, 242. Here's a sample, 225. Here's a sample, 215, and here's a sample, 350. We could pull each one of those as a specific sample. But if we were to take the mean of those, we would find that it is 242.4. Well, that's great, but what happens if we were to take samples of size 2 or samples with size 3 or samples with size 4? And we find that while each sample would have a different mean, the mean of all of those samples is exactly the same. So the population mean is the same as the mean of all of the possible samples. Okay, and that works for any problem that we have. So we can use that information to help us say, well, we can then therefore use uh, sample means as an estimate of the population mean. So that helps us figure out, well, which ones are we don't have to worry about going, well, gee, the only way we can figure out this thing out is having the population mean. We can have sample means, and that's very helpful. Um, and what they're saying here is that populations are huge. We knew that. We represent population mean with the mu, which is a Greek letter M. Um, if we have a sample mean, we can use that as a way to estimate for the population. And because it's not exact, there's error, and they call it sampling error. So here's 2 things. Sampling error is the error that occurs because we're taking a random sample of a population, and therefore we're not going to get the perfect mean. And when we write out these things, n stands for sample size, which we already knew, mu stands for population mean, and x bar is the notation for sample mean. And remember, to get the mean, we take all of our samples and we divide by how many things there were. So here, for example, they took a survey of 400 students, and you can see all their values, and they asked how much time do they spend using a search engine per week. And of those 400 people, they got a mean of 3.88 with a standard deviation of 2.4. Sorry. So if they were to sample 32 people, they would get this group here, and they would say, okay, well, let's find the mean of that. Well, the mean is 4.17. Okay, and it's the sample mean is a sample statistic because it's a statistic that we've calculated, and it's a sample piece. So we found this specific sample mean. Now we can do a different one, and we'll get a different mean. In this case, 3.98. So they don't necessarily have to be the same, but notice they're not exactly the same as each other or as the population mean. They are estimates. Some are better than others. Notice the second one is closer to the population mean than the first one is. Some will be high, some will be low. And here, what they've done is they're showing you is that if they took 100 of these sample means and they did a histogram of them, well, notice they fall generally with the population mean. Here's 3.88 is somewhere in here. So there's a fairly normal curve. okay, where with the mean of the sample means being fairly representative of the mean of the population mean. And that's what they're trying to show you. So the other thing we have is distribution. So when we have, let's get all this out here. Okay. The distribution was really the histogram, and they should be normal. They should approximate the normal distribution. They should have a mean close to the population mean. So this is why we can use, again, they're just trying to show you reasons why we can use the sample mean to estimate the population mean. Well, that's really all they're asking about here in 8.1. The reason we're going to do that is because in 8.2 we're going to do some more stuff, and then in 9 we're going to do some more stuff using only sample means as opposed to population means. So if we have a sample, and in this case they were all sample size of 32, the sample means would be approximately normal. The means would have the means of the sample means would be 3.88 approximately. And the standard deviation will be the population standard deviation divided by the square root of n. Because remember, when we're dealing with samples, means of samples, remember we did this in chapter 6, we did with the central limit theorem. We used the square root of n to divide by that because we're going to have smaller samples, we're going to have smaller distributions than we would overall from the population because we're taking samples, we're taking means of samples, and we have lots of them. So it's going to be closer and closer to the actual value. So the standard deviation is going to be smaller. All right, and here they've done another one. Okay, they have another 32 group, and this time they got a sample mean of 5.01. Well, we can calculate the z-score of that. All right, and see how likely is this to occur. Well, remember, to find the z-score, you take your sample mean, subtract off your population mean, and divide by the standard deviation. Well, in this case, remember, we are having sample means, so we have the population standard deviation divided by the square root of n. Well, they already took that into account here. So we have our sample mean, we have our population mean, and we have our square root of standard deviation divided by the square root of n, and when we do that out we get a 2.7. Now 2.7 we can look and see, oh gee, that's already bigger than 2, so we're an unusual occurrence. We're at almost 3, so I mean that's a very unusual occurrence. And here we can look it up on the table, and you can find that according to this it's in the 99.65th percentile, which means that the probability of finding something less than 5.01 is 0.9965, and the probability of finding something bigger than 5.01 is 0.0035. So the chance of finding something even larger than that is tiny, and so the chance of it occurring is tiny. And so this is a very unusual occurrence for that sample. But it is a possible sample to have picked. So that's something you just need to be able to realize, because we're going to use this information to this specific idea here to figure out information coming in the next couple of chapters. And here's one more example. We have farms, and they want to see what is here's this farm sizes. There are 582 acres, so standard deviation 150, and they're going to sample 100 farms. And they want to find the mean and standard deviation of those sample means. Okay, so what is the probability of selecting 100 farms with a mean greater than 600 acres? Well, this gets back, remember, to the normal distribution and the central limit theorem. We're just still beating that up at the moment because we need that information for later on. So if we have 582 is the population mean, the standard deviation is 150, n is 100, remember we're going to have to do x, or in this case x bar, minus mu over the standard deviation divided by the square root of n. So here we go. They found the standard deviation of the sample standard deviation is 15. They plug that in. They get 600 minus 582 over 15, and they get 1.2 as a z-score. We looked that up in our table, and we find that it's in the 88th percentile. This isn't 5.1. Okay, they're still using that one for this. We could also look in table A, which is what I would do. So finding something less than 600 acres is 0.88. Finding something more than 600 acres is 0.12, because remember, these things have to add up to 1. So that's all of a